Hi everyone, this lesson is about a particular topic in differential equations called slope fields or gradient fields. So here's a differential equation, dy over dx equals x, and we've been asked, or we're going to plot the slope field for this differential equation. Now this is the way we would do this. We would set out a table of x values and then dy dx values. Typically we would go from about -3 to about +3. Now in this case, dy dx is exactly equal to the x coordinate. Dy dx has no dependency on the y coordinate. So if I was to try and plot this field, then I'd need a grid. It's a bit rough. There's my y-axis, there's my x-axis. So that's the origin there. Now, when x equals 0, the gradient of this function equals, or this field equals 0. So I'll put a short red line with 0 gradient everywhere where x equals 0. When x equals 1, the gradient is 1. So I'll put a short red line with a gradient +1. When x equals 2, the gradient is 2, so that's somewhat steeper. When x equals 3, it's very steep. -1 over here, -2, so very steep, and -3 would be even steeper. Now that's a very rough, difficult thing to draw. So I prepared one earlier. Here it is. I wonder if I can just put that over the top of my drawing. Oh, of course it's transparent. Oh well, I might just obliterate my drawing then, because well, my drawing was really a bit too rough, wasn't it? But that's the idea of how these slope fields are generated. Now, I've used a piece of software called Geogebra to draw this diagram, which is very neat and very accurate, and that's really the way that this would always be done, with software. So let's just, here we go, let's just move this one a little bit. Let's take a look at this slope field. So as we can see, everywhere where x equals 0, these little short lines representing the gradient would be 0. Now this doesn't represent a single function. Because a differential equation has a whole family of different solutions, all the solutions, possible solutions, are represented in this diagram. Now let's have a go at solving the equation. If we had dy equals x dx, and then we integrated both sides, we would have y equals x squared over 2 plus c. So you could literally have any equation, there'd be a parabola. Now we did say that the initial conditions suggested that when x equaled 0, y equaled -3. So the particular solution in this case would be x squared over 2 minus 3. Let's see if we can sketch that. When x equals 0, y would be -3. If x equaled 1, this is 1 over 2 minus 3, so that's -2.5, we'll be here. When x equals 2, 2 squared is 4, 4 over 2 is 2, and 2 minus 3 is -1, so we're here. X equals 3 squared is 9, 9 over 4 is 2 1/4, 2 1/4 minus 3 is 1 1/4, so about here somewhere. Let's do 4. X equals 4 squared, 16 over 2 is 8, and minus 3 is 5, so we're way up there. Certainly looks like a parabola. Here we go. Rough sketch. and off it would go. And there'd be a symmetrical curve on the other side. Oh, that's pretty horrible, wasn't it? Now, let's pop over into Geogebra and have an accurate look at this. Oh, there's my slope field. So we suggested perhaps that I should have had a function of the form y equaled 0.5 x squared. Now that's assuming it's 0 there, but minus 3. That's the solution that we were looking for, and it fits within the slope field. You can see that, you know, the slope, each of these, at this point here, the slope of my line is 1. At this point here, the slope is 2. At this point here, the slope of the line is 3, and so forth all the way around. It is not the only solution, I should say. We could, if I just go back and define that function as 0.5 x squared, then I could have an entire family of solutions here. I could have f minus 1. Why didn't you do that? Maybe I had to go y minus 1. No, I didn't like that either. Let's try again from way back up here. Let's define this as f of x equals 0.5 by x squared. Now we'll see if we're happy with an input of f minus 1. That's better. F minus 2. F minus 3. That's the one that we were looking for in our example. All of these parabolas are solutions to, or potential solutions to, the differential equation dy over dx equaled x. And that produces, as you know, a whole family of different possible solutions. The generic solution would be 0.5x squared plus c. But we knew better when we were given our particular question here. We were given this little extra clue here that allowed us to pin down a specific solution out of all the different general solutions. Now, just before we leave, you might like to know how to generate these diagrams for yourself using Geogebra. So let's just start a new worksheet. Don't save that. And here we go. So the command that I need to create a slope field is, yes, very surprising, slope field. Now I use this last one here where there's lots of different parameters that we can control. Now this is where we put in the differential equation. So we had dy over dx equal to x. I'll just put x. The number, I'll put 11, you'll see why in a minute. Length multiplier is between 0 and 1, 0.5 gives nice little ones. Minimum x, let's go from minus 5, minimum y, minus 5, maximum x is 5, maximum y is 5. And this gives me a nice neat little slope field. Now why did I need to say 11? Because there is actually 11 little entries across here by going from minus 5 to positive 5. And this way they're all neatly on the corner of a grid. Now we didn't have to have dy dx equaled x. We could have had something more complicated like dy dx equaled x multiplied by y. Look at that for a beautiful little slope field there with all those interesting things. It would be interesting to try and solve that differential equation and see what sorts of functions we would get. So that's it for the introductory lesson on slope fields. I'd encourage you to try as many of these exercises as possible using Geogebra, but of course in an exam scenario you wouldn't have Geogebra, so you should be familiar with this idea of plotting them out for yourself, even if we don't do as much, just to a few points either side. Okay then, thanks for watching.